Okay, so quick review. What we're going to do today and what we did in our last class is we went ahead and we were focusing on second derivatives. Okay. And specifically with second derivatives, what concavity versus an inflection points can actually be applied as. Why would we care? The word application. You know, like I said last time, talking about a minimum or a maximum, that's a pretty natural application that we're already like, oh yeah, the minimum of something, the maximum of something. Where is something increasing? Where is something decreasing? All that's kind of normal. But we don't hear people talk about, well, where is it concave up or where is it concave down or where is there a point of inflection? But yet there are times where those things are actually important or discussed in the context of a function model. And so we focused on that last time, specifically with the concept of that point of diminishing returns. And we're going to pick up with that again. We're going to do an example of a diminishing return again to start things off, and then talk a little bit more generically about concavity and points of inflection and their focus, their applications. Okay? So that's today. Our next class then is Tuesday. We're going to do a little lab project, just a little in-class one, nothing big, but something to do to review, to work with more concrete applications of the concepts that we've been studying about increasing, decreasing, mins and maxes, absolute max, absolute min, concave up, concave down, points of inflection in the real space. So little lab assignment project we're going to do in class on Tuesday. Thursday, more of sort of overall review. And then, as weird as this sounds, because of an additional 4-day weekend, that following weekend, the Wednesday day is when we're going to do our Unit 3 quiz. All right, so once again, today's the 13th, and so on Tuesday this is the 18th, this is the 20th, and then 26th. Unit 3 quiz, like I said, that's going to fall in between two deadlines I have for quarter/semester grades. And so if your grade is sitting at the borderline, I will definitely look at your quiz and see if it will be something that will help you. And if it will, I will make sure it is in your semester grade. If it doesn't really, if you're not on a borderline between two grades where this might bump you to the higher grade, then I probably won't make a concerted effort to get it into the SIS for second semester or for second quarter. It'll just go in there for third quarter. It's a rolling grade book, so honestly, in the big picture, it doesn't matter. But I know for seniors, where we end at the end of first semester is a little bit more significant. So I'll make sure if you're in the scenario where this is super important for how things look, that you get the benefit of it. Okay? Questions about that plan? Okay. So that's still the plan until it snows again, and then it's not the plan, and then we'll go from there. Okay. All right. I have gone through. I've checked some missing work that people have turned in. I'm still finishing up that last assignment you did right before break. And I did mark in SIS, though, whether or not I had received that assignment from you. So you might check SIS and see if you have a not turned in for the Unit 3 review form before break. You might see where that is, get that taken care of. I'm wrapping up grading that and getting that in. And trying to think anything else. I don't know, just if there's anything else that we need to talk about. I know I've talked to individual people about certain things grade-wise, and we'll just remind me, and we'll work on whatever we can to get things neatened up here. Hard to leave and come back, and then obviously harder to have an extra week, but we'll get it all fixed up and organized before my final due date for grades. Okay? All right, review problem. You are going to need some paper for today. We're going to do a review problem, and then we're going to take a few more notes on concavity and inflections. So if you have room on last class's notes, you can probably add on to this. It's not quite as much. And then we'll do a short assignment. So I'm going to all right, so in this particular function, again, X is going to represent number of dollars spent on advertising. R is going to represent dollars collected in revenue, both of those in thousands. And so my question for you is to find the value of X where the R, or revenue, is increasing at the greatest rate. Okay. So that is exactly what we did last class. It might not have the exact language, but that was the additional language we talked about, that the point of diminishing return is where, when we have that change in concavity in an increasing function, diminishing return point is where the increase or the growth is happening the most quickly. It's increasing at the greatest rate. So a diminishing return point is this particular point given a particular fixed interval, because it doesn't really make sense to talk about negative advertising dollars, okay? So for the minimum of 0 advertising dollars and a maximum of 6,000 advertising dollars, if these are our options, if that's our range of options, at what point in that interval would be growing our revenue at the maximum rate? Yes, ma'am.
So, like, how do you find the 6, or is that just going to be what's given?
That's going to be given.
Oh.
Yeah, so this is all given. So this is a given set of restrictions for you to know that we're only looking in between these numbers. So when you create your number line, it's not like infinite. Honestly, if that wasn't given, it wouldn't necessarily, well, I mean, it could. You could have, it really wouldn't affect things very much. It's more just for the reality of the problem. So diminishing returns, second derivative, critical value, concavity, concave up to concave down specifically. Oh, I remember something else. Oh, something else I'm supposed to remind you about while you're working. I'll just pop this over here. Just a reminder that if, at least in theory, right now, what we're being told is that any more snow days that we might have may end up being actually virtual instruction days, not the fun kind of snow days we're used to. The school board had agreed to 5 regular kind of snow days, and we burned all 5 of those. So if we do have a snow day, and if the directions are that we are having a virtual instruction day that day, and it happens to be a B day, then I need to make sure I show you and remind you in our second period Schoology, on the left-hand side down here towards the bottom will be the link, like we did with last year with Blackboard Collaborate Ultra. We don't have a contract with Blackboard anymore, so our video vendor is now Zoom. And so when you go to that, you should be able to click on that, and that is where you would get into our class. That was what I was asked to share with students. I have no additional information about if that will honestly be the plan if it's a snow day. It might end up being an asynchronous day. I have no idea. They don't really tell us very much of anything. And anything they tell me, I'm telling you. So that's all I know, is that I was told to be ready, to make sure I had my link ready, and to make sure you guys were aware of where that link was in Schoology, so that if we were thrown into a scenario where we had to go virtual, that would be available. Also, if we do get hit and we start getting multiple people on pause, I'll be able to live stream with that. And so if you're going to be out of class but want to log in during our class time so you can stay on top of things, that will be, I'll make sure, let me know, and we'll just run that and it'll be fine. It won't affect anything. You'll just be able to hear my nonsense at home. I'm also recording, so I'm trying to be better about doing that on a regular basis. If you're going to be out, giving me a heads up and sort of tweaking me, making sure I record, always a good plan. Okay, so let's roll this guy. That's that. Okay. So my R prime, let me look at my R. So my R prime was negative 2x squared plus 16x. Hopefully we're super experts at that. No fancy schmancy product rule or quotient rule or chain rule, just basic power rule on polynomial terms. There's my second derivative. Set my second derivative equal to 0. Also kind of good, just to come back to the point about the 0 to 6, if you have that set of restrictions, that's a good kind of clue that if you get a negative x, you're clearly in the wrong, doing something wrong. We should be getting an x between 0 and 6 here. And so that's kind of like a little safety net where if you make a sign error, you go, oh, wait, yeah, that doesn't make sense. Okay. So x equals 4 seems like that's going to be what we want. We'll double check it with double check a sign check around 4, specifically between 0 and 6. If I look at my second derivative values are positive and then negative. So that must mean when I go 0 to 6, that turn in concavity, that shimmy, is at x equals 4. So at x equals 4, which represents $4,000 in spending, on ads, revenue growth will be at the greatest rate. Okay. Sometimes it's not about being at that point, it's about being close to that point. So we know if we're spending like $3,500, $3,500, if we're spending in the range of $4,000, those are still powerful advertising dollars, and that they're growing our revenue, and they're growing our revenue aggressively. In economic theory, once we're up here, it's not that we're not growing, but we're just not getting as much return for the dollars invested. The dollars we're investing down here are giving us more return than the dollars we're investing up here. The dollars we're investing right around here are the most powerful. So anything past here is considered a waste, and would be think, okay, we've got limited resources, so maybe these dollars we put somewhere else to something else that can improve revenue. Okay. They're still going to give you more revenue. You're still increasing, but just not as quickly, not as in a most efficient way as down here. Okay. That's a diminishing return. The payback for what you're investing is less, is diminishing, getting smaller in this area of the curve versus this area. All right, so that was what we did last time. Questions? Things still kind of, we're going to review that again. We're going to do another one of those in a little bit, but okay. So that's one like really specific second derivative concave point of inflection application in one case, in an increasing function, concave up to concave down. We can actually have lots of combinations of increasing and decreasing and concavity that we can talk about a little bit more generically. So not necessarily what happens at one specific point, but what little pieces of the curve are like and what they represent. And so that's what we're going to look at today, is to talk a little bit more about just generically how to do an interpretation of a function using a second derivative. So this happens really naturally with first derivative, because a first derivative is a function's slope. And so very, very early in this course, when we started to identify the concept of the first derivative or the derivative, and we learned that derivative and slope were the same thing, that derivative was code for slope, it's calculus slope, we knew, or we very easily connected to, that if we got a positive number for our first derivative, that represented that the function was increasing at that particular value. Okay. So for example, let me throw something out here. Let's do a function. So negative 1.9 t cubed plus 41 t squared minus 58.6 t plus 3972. In this function, t represents the year. And we're using our standard 0 year being 2000. And S representing sales. In millions of dollars. Fine for me. What S prime of 5 would be, and tell me what it means. Find S prime of 5, and tell me what it means. Like I said, I know you're like, what? But I know you don't believe me, but you have done this a lot of, and some of you are like, yeah, I've done it, but I'm still not very good at it, but that's okay. That's why we're doing it some more. What does S prime at 5, when you get this answer, what does it represent? What does it tell us about S? Go a little double box here. So I can look at my S. So S prime, that's 7. So negative 5.7, not a T. Oh yeah, it is a T. T squared. Plus 82T minus 58.6. All right, so there's my S prime function. Remember, you have to find the function first. S prime, the derivative of S, and then evaluate it at 5, which is definitely a calculator action. Make sure I didn't mess this up yesterday and they just didn't tell me. Let me double check myself. Negative 5.7 times 5, where 5 is squared. Don't forget about order of operations. 58.6. No, that looks like I'm right. Okay. All right. 208.9. What did we just get? First of all, S prime at 5 is positive. So what does that tell me about S around x equals 5? S prime, number line. I plugged a 5 in. I got S prime to be positive. So what's S doing? What's happening to S around 5? It's increasing, right? Positive first derivatives mean things are increasing. So S is increasing in 2005 by 208.9 million per year. Okay. It's a slope. It's a rate of change. So it's the change in S compared to a change in T. It's a little weird because you're like, you're not really changing T. You're just doing 1T. It's a slope at a single point. That's what a derivative tells me. If we get if we measure the slope of the S function at 5, the slope of the S function at 5 is 208.9. It's a positive slope at 5. That means that the thing that S measures, which is the sales, those sales are increasing in 2005 at a rate of, or by, 208.9 million per year. Okay. Increasing, positive slope. Positive first derivative, increasing. Okay. If we had gotten a negative, that would tell me S was decreasing at that year. Okay. So if we could look at the graph of S, we would expect the S graph to be uphill. I'm not going to make it right now because it'll take time, but the S graph would be uphill at 5. And if we could draw a tangent line and estimate that slope, it would be like about 208.9. Okay. So that's kind of the part we sort of knew. Okay? We knew positive slopes meant increasing and negative slopes meant decreasing. Okay? We may have not connected it exactly to this increasing and decreasing that we've been talking about, but it's the same kind of thing. Okay. Let's talk about S double prime of 5 now. Okay? Find that value for me, and then we'll talk about what it means. Awesome. So much nicer when the internet works, especially since we're so dependent on it. Yesterday, that was the worst. It was like, couldn't take attendance, couldn't do anything. It's like, I'm going to do this. No, I can't do it. I'm going to change grades. No, I couldn't input grades. I couldn't do anything. All right. So S double prime. Negative 11.4 t plus 82. So S double prime of 5, I'm getting why don't I, 25. There it is. All right, so S double prime positive means what shape of graph? A positive second derivative. Second derivatives measure concavity, so a positive second derivative is what? Concave up, concave down. Concave up, concave down. It's going to be up. It's going to be up. So we know, basically what I know right now is around around 5, around t equals 5, that my S function looks something like this, where t equals 5. So S prime is positive, means we were increasing. S double prime is positive, which means we're concave up. So what does that mean in terms of the sales function? in 2005, the sales are growing. Okay, that was from the first derivative. Make sure I'm consistent with my language here. At an increasing, and I could have used increasing both ways, at an increasing rate. Their sales are growing, and the rate of growth is also growing. Positive first derivative, positive second derivative. Typically, when we're going to talk about a second derivative, we need to talk about what it's going to mean in correlation with the first derivative. First derivative by itself tells us something. Second derivative all by itself gives us a piece of information, concave up. Okay? But what does concave up mean? Well, concave up with increasing means a certain thing. It's the combination of the first and second derivative results that tell us, that give us an interpretation of the function model. Okay. There's essentially four things that can be happening on any kind of basic curve, well, not even curve, if it's straight, basic function model. We're going to look at all four options. And if we want to continue here and just add something else onto this, because you're like, well, what about the answer? They're growing at an increasing rate of 25 million per year each year. It's like meters per second squared. It's acceleration. It's growth. It's growing and accelerating with a positive acceleration. 25 million per year, every year. So not only are my sales growing, but the amount that it's growing is growing. And if you're sort of stuck on like, well, what do you mean? Well, that would mean if we were looking at sales, let me throw a 5, 6, 7, okay? So let's say this is T and these are sales. So let's say if this was 4,000 in millions of dollars. What did we say that increase was? Oh, this is what happens when I start trying to do stuff on the fly. There we go. So like 200. So maybe this is like 40, 200, but then this is like 450. I'm just going to kind of give you an, and then this is 40. Okay. So growth, well, we can see that. Yes. S is getting bigger. But let's make that different. I want my growth to keep getting bigger. Let's make that 4,800. Sorry, this is me making stuff up on the fly. So that would be a 250 growth, and that would be like a 350. So it's getting bigger, and the amount by which it's getting bigger is getting bigger. The fact that this is getting bigger is the first derivative. The fact that the difference in those numbers is also getting bigger, that's a leap of 50, but that's a leap of 100, that's the second derivative. First derivative measured here, described here, second derivative described out there. Okay. looks so much neater when I write that in fourth period because I've already thought it out. Anytime I wing it, it gets weird. All right, so what are the different combinations? Well, this could be going up or down, and this could be up or down. So basically, four things can be happening. Let's take this off a dual because I'm going to need one big page. So I'm going to make basically like a chart here of four different shapes. We'll talk about something like this versus something like this versus something like that versus something like that. All right, good work. Okay. So in my first row going across, in both cases, we have an increasing curve. From left to right, the values are getting larger for y. The curve has a positive slope. F prime is greater than 0. This is also concave up. Or F double prime is greater than 0. So what we would say about this model is in this area of curve, we are increasing at an increasing rate. We're growing, and our rate of growth is growing, and probably eventually we're going to hit a diminishing return point where we're going to turn. Okay. If we're growing, but concave down, with which means second derivative is less than 0, we are still increasing, but we're increasing at a decreasing rate. And unfortunately for everybody, we've lived those two graphs. This is where we were in March of 2020. We were on this kind of curve, and we were trying to turn it into this kind of curve. We weren't going to be able to stop it from going up. We knew that. We didn't have a vaccine yet, so we didn't have a lot of things we could do to stop it from growing, but we were going to try to slow the growth. We were going to flatten the curve, which essentially meant we were trying to get it to turn. Part of it was to get it to turn from being concave up to concave down. Slower growth versus quicker growth. Still growth. We knew we were going to have growth. But it was to slow the growth. And so it's the social distancing and all the things we tried to do or did, to keep that curve from spiking up like that, and to hopefully either go longer this way. So that was one thing, is to pull it this way, but then also turn the curve and hopefully stay under. We had a lot of graphs we looked at had a line and said, okay, this is our capacity for our hospitals and things. And that was pretty much our main focus. It was like, we knew we were going to get people sick. It's just how sick were they going to get and how quickly were people going to get sick, so we could keep them under that line. Your kids are going to learn about that in school, and you're going to be like, yep, I lived it. All right. Yeah, unfortunately, we had a front row seat to increasing at a decreasing rate, or at least we wanted to. Okay. Now, other two things. If we get a curve that's decreasing, okay, where f prime is negative, where we get a section of curve where f prime is negative, but we are still looking at concave upness. F double prime is greater than 0. For me, the best way to describe this is to say we are decreasing, but the decrease is slowing down. It's dropping faster over here than over here. This is a quick drop. This is a gentle drop. If you think about it like a roller coaster. When we have this kind of downhill, this steep part is where the drop is happening quickly. This is where the drop is happening more slowly. So the easiest way for me to say that is the decrease. It's decreasing, but the decrease is slowing down. Okay. We have a slower decrease down here than up here. Basically, it's whatever, when these are opposite of each other, whatever this is doing, we're slowing it down. So a negative first derivative and a positive second derivative, oops, that's not right, I need all over it, kind of work against each other. So we have a downhill situation, but a downhill that's slowing. Versus this guy, where we're decreasing, but we're concave down. And my decrease is speeding up. You know, this is when you go down the hill and it's kind of flat and then you drop, okay? So two different kinds of scenarios here, you know, slow drop, and a lot of times that's when you kind of like hang and then you, okay? So that severe drop is when we have a decrease with a downward concavity. So we have the rate of decrease is going to get bigger. It's going to decrease more quickly. It's a little tough because we start talking about absolute values, so I'm just not even going to get into that conversation. And I'm going to say that this language tends to be what I find to be the most successful for us to use in describing these two different situations, or 4 different situations. So on our sales problem, our sales were growing at 2005, and the rate of growth was also growing. Both first and second derivatives were positive. A little bit. Okay. When would the sales be growing the most quickly? Find that for me. When would be the most rapid? When would the sales be growing at the greatest rate? When we take a look at that, let me move this, and let me find my fun graphs. There we go. Okay. If we start talking about the greatest rate of growth, that's back to diminishing returns. So if I look at S double prime equal to 0, it's growing at a growing rate at time 5. Just the question is that when it's growing the most aggressively? And I lost that paper. It's over here. Here we go. All right, there we go. Let's make sure I don't mess this up. So negative 11.4 t plus 82 equals 0. Yeah, not going to be a pretty answer. I'm getting t, when I finally divide that, is like at about 7.913. So in 2007, my sales are going to be growing at the greatest rate. If I do a doubled prime, 7.913, 2007, you know, almost 2008. Based on this data, we have a positive second derivative, and then we have a negative second derivative. We have an uphill. So the 5 was about here, and that 7.912 or 3-ish is about right there. Sometimes this kind of analysis is done for predictive reasons. Sometimes this kind of analysis is done for, you know, you collect data about the past, you look at the historical data, you maybe talk about like what happened, what was going on at different places, because then you're going to try to replicate that, or you're going to, you know, I don't know. Okay. Or maybe you're doing something similar, you're starting a new company, and so you're looking at this company's data from the past and looking at the trends that happen and trying to talk about why certain things may have happened when, and so on. Okay. Lots of analysis available for data. So your job in the next assignment that I'm about to give you is to do, well, I have a diminishing return problem for you to do, and then I have a second problem for you to do where you're going to look at, for a particular function, a first derivative, second derivative combination, and tell me what that combination of information will tell you about the function. The first derivative should tell you about whether the function's increasing or decreasing at that particular value, and whatever the function represents, then you have a context. And then, is it increasing at a growing or slowing rate? Is it decreasing but slowing down? Is it decreasing but speeding up? Right. This chart is going to be kind of the most important part of answering that second set of questions. So, here is your problem, 2 problems. You're to do these 2 right now. There's one diminishing return question, the one first second derivative combination analysis question. You do these and turn them in now, or if you have to finish it after you leave and bring it back to me next week, you can, but you might forget, so don't forget, or do it now. Plenty of time to do it now. Yes. Yes. Okay.
Absolutely.